Let me announce our last speaker, László Lovász. And I was thinking to say some relevant sentence of László's contribution, but I have realized that I am although you know, check better than me, László is extraordinary. Oh, I don't say that. But I say at least once. Here in Budapest, we work, we have been working. We are very well. And we return to us. This is one thing. And another thing, I mentioned the importance it used to show the next generation, and now, and even further next generation. László Lovász won the first prize in high school, mathematics high school competition and the physics high school competition this year. Not this László Lovász, his son. Okay, so
Speaker at such a long and exhaustive day has advantages and disadvantages. The advantage is that I can thank András for organizing this. I think it has been a very important event, and I certainly had great pleasure to participate, and I know that András put some enormous effort of putting all this together. The disadvantage is that, well, first of all, everybody is tired, and second, a lot of things that you wanted to say has been said, so it's difficult not to repeat observations and thoughts about the significance of these methods. So I changed actually my title a little bit. I wanted to talk about matching structure, but it seems to me that to go into one more technical aspect of the subject would be too much. So I would instead just talk a little bit about my experience with matching theory. So, of course, it all starts with bipartite matching and Hungarian method, and I was always fascinated with matchings, and this eventually led me with my plumber to write a book about matchings. And while we were writing the book, the one important thing that we noticed was that if you do something and develop, look into the ideas about matchings, they usually lead to much more. So matching, especially bipartite matching, König-Hall, atomic path, Hungarian method, is the starting point of an enormous number of branches of modern discrete mathematics. And so by writing the book, we tried to do this, and we did some search and tried to follow up these paths. And actually, maybe I'd like to tell a story that this whole project had one very critical moment. So Mike Plummer was visiting me in Szeged, and Mike did a really terrific work about collecting and annotating the literature. And so we had some hundreds and hundreds of pages of annotated matching literature, which he brought along, and we were working through it. And one morning, my daughter told me at home that they have a paper drive in the school, and so how can I help her? And I said, okay, I can go down to the computer guys and ask if they have some computer paper. At the time, the computer paper was produced in quantity, so it was always easy to get. And I said, it will wait you in my office even if I am not there. And so I forgot about my promise, so we went off for lunch, and we came back and chatted a little bit, and okay, so let's continue working with my plumber. And then we didn't find the big pile of annotated matching notes. And I mean, the lucky thing was that I realized what happened. And so we rushed to my daughter's school, and there was a long line of kids, each having a big pile of paper, and there was a truck, which was stepping to the truck and throwing the paper at my daughter was maybe tenth in the room. So, well, except that of course, while running, I had to pass by the computer guys and pick up an equivalent amount of paper. So anyway, we managed to salvage the material, and actually managed to complete the book. And so let me talk a little bit about some of these branches, some of these areas that open up from this core. So bipolar matching itself has some very history which goes back to the early 1900s. I think the first theorem that's equivalent to the merit theorem was proved by Frobenius in 1917, but many other matching results were proved in the years before. I don't want to go into the interesting story of Frobenius and Koenig's work here. You can read about it in many books. And of course, polynomial time algorithm, which we are celebrating today. There was also a structure theory, and it's a less known work of Koenig, who actually in 1916 studied the structure of perfect matchings in a given graph. Which edges belong to perfect matching, which just do not belong to perfect matchings. This all came from trying to understand the connection with perfect matchings and determinants, which I will come back to. So, actually, Frobenius' work was on determinants, and that's how he got interested. I mean, he never got interested in perfect matchings, but he proved theorems which today we consider matching theorems. Also, fairly early structure theory, a more detailed structure theory, was worked out by Damage and Manus. So, of course, the first continuation of this work was extended in bipartite matching. And the existence was proved by Cotton. I think I forgot to add the dash and prove the corresponding min-max. And the polynomial time algorithm, of course, was elaborated. The Blossom algorithm of Jack Edmonds came in 1965. And again, structure theory in various senses was worked out by Gavai, Edmonds, and actually for graphs which, these two are for graphs which do not have a perfect matching. And then structure theory for graphs with perfect matching was started by Hotzing in very early also. Very nice, maybe not so well known work. So these are all known things. Let's look at another continuation, which is alternating path in different settings, not matchings. And I will just skip through this because this helps. During this conference, we heard about lots of these extensions and all sorts of very interesting algorithms that are based on the idea of alternating path. Internet programming is, for me, also very closely connected to matching theory. I was was seeing Tibor Galai regularly when I was a student, and he taught me all sorts of beautiful mathematics. Among others, he was the first one to tell me about linear programming, and said, it's a very quiet way that, you know, it's not everything is really deep in it, but there is the duality theorem. That's very interesting, and also its connection with matchings. And then later, when I took a course on linear programming, I actually didn't have to take an exam because the professor said that if you derive anyone who can give a proof of the matching theorem based on the duality theorem, a correct proof in all details, and gets an A, it's called an A. But anyway, the extremely important ideas like total unimodularity came out of this, and total dual integrality, and of course here somehow in these lines one could also mention perfect graphs. And all these, like total unimodularity with the work of Paul Seymour is really one of the centerpieces of a lot of very deep mathematics, decomposition theory for regular matrix. Polyhedral combinatorics is closely related to linear programming, but it of course takes a different approach, and that's more or less the area when I already grew up. So I learned about Edmonds's description of the matching polytope, probably 69 or something, so not too much later, and it started a whole industry of describing all sorts of interesting combinatorial polytopes, and eventually I also sort of got very interested in this and spent about maybe 8 years of studying all sorts of connections and applications of this idea. Again, the matching polytope was one of the first really non-trivial applications where one could exhibit that the equivalence of separation and optimization principle on the Martin and Flags, that was one of the first non-trivial applications of this. So this is the part I didn't want to talk much about, and now let me come back to the idea of determinants, which goes back to Frobenius, and it was Koenig who pointed out the connection of the determinants with matchings. So what is this connection? I'm supposed to be a math talk, so I want to put up at least one or two slides with some formulas. So here is the adjacency matrix of a graph, and I marked with red the edges. It's a bipartite graph, so it doesn't have to be symmetric. It's just adjacency matrix of a bipartite graph. The rows correspond to one class of nodes, the columns correspond to the other class. The one means an edge. The red ones, if I did not make a mistake, give a perfect matching in this graph. Let's think of this, to modify this matrix by putting in, it will be clearer, the connection if we put in just any arbitrary numbers for the ones. We keep the zeros where they were, but we replace the ones by separate variables, and also marked by red. They dictate the color. So, and then very simple basic observation is that if you take the determinant of this, then you expand it, then it will have an expansion term corresponding to the red entries. The product of the red entries will be an expansion term, it's some sign. And it's also important that this particular product occurs only this once. So it's not cancelled by any, at least not formally, not as a polynomial. Now, this brings up the idea of, well, maybe we can use this to actually say something about perfect matching. So, for example, this determinant is identically, if this determinant is identically 0, then no such term can be, and therefore there cannot be a perfect matching. So this means that to test whether a graph has a perfect matching is equivalent to testing whether this determinant is identically 0. Now, if you go to high school, you know it's a polynomial, you know how to test that the polynomial is identically 0, you just expand everything and see if everything cancels. Now this does not work, of course, because expanding it would be equivalent to actually listing all particular bijections and seeing if either one of them is a perfect matching. So that would be the algorithm which is the very bad algorithm. So n factorial, very false. Actually, there's an interesting to comment on the history here. This was not what Frobenius started. He looked at such determinants and he asked under what condition is such a determinant a reducible polynomial, and under what condition is it an irreducible polynomial. And he proved that this is an reducible polynomial if and only if it has, after appropriate rearrangement of the rows and columns, it has a block of zeros which makes it sort of block diagonal. Then of course it would be this determinant times that determinant. Now you can ask why, and then König gave proof of this based on this correspondence between expansion terms and matchings, and then a graph theoretic description of matching. And then Frobenius didn't like this because he thought it was an algebraic problem and combinatorics should not have anything to do with it. And he gave another proof. König's proof was substantially simpler than Frobenius' original proof, but then he gave a simpler proof. And in this simpler proof, he formulated a lemma which says that this determinant is identical to 0 if and only if there is not a k by n minus k plus 1 block of zeros. So, looking at it today, it seems strange that why do you ask first when is this polynomial reducible, and why don't you ask first when is it 0? But when is it 0 was an irrelevant question. You learned in high school how to test a polynomial whether it's 0 or not. To decide irreducibility was algebraically interesting question. Today we sort of think that the more important basic question was whether this is identical. So this connection was discovered by König, and that extends to non-bipartite graphs. You have to replace the matrix by a skew-symmetric matrix, and then there's a very similar, more complicated correspondence there, which was discovered by Tott. It's interesting that it's in the same paper where Tott proved the Tott theorem, characterizing perfect matchings, and he used this to prove something which actually is fairly easy to prove directly. So somehow this paper contains two ideas about how to treat perfect matchings, and somehow the combination of the two, but they separately have their value. Perfect in 1966 proved correspondence between the rank of this matrix and maximum matchings. And Edmonds in the next year showed that you can actually just take linear algebra and use linear algebra to decide. So apply linear algebra to the question of is this determinant 0 and get a proof of the marriage theorem bipartite matching out of this. I still don't know a proof of Tutt's theorem on these lines. If anybody does, I would be very interested by it. It seems to me that there ought to be such a proof. Now this idea of, okay, so first I forgot to say something. It's sort of obvious that this question of reducing, okay, so there are many other questions actually that can be reduced to here is a determinant, is this identical to 0? There are many questions in rigidity theory and theory of geometric representations and elsewhere. Electrical network theory, numerical analysis, and so on, which can be reduced to these questions. So it's a very fundamental, it turned out to be a very fundamental algorithmic question, so its complexity is still unknown. Given a polynomial, given say, a determinant, is it identical? So, now this idea of determinants, first of all, leads to randomized algorithms for matching problems. And now this is a very different type of algorithm from alternating paths. So here we get something which is a different approach. So far we have seen that alternating paths are all over the place. Well, there is something else here. Well, the randomized algorithm, okay, algorithm consists of basically two virtual substitutes. So random substitute random values, and was pointed out by Edmonds for bipartite graphs, and I think precise analysis of the running time takes a little work, and it's basically Schwartz in 1978 who proved the Schwartz lemma, which is used in this analysis. Let me mention that there is a version of the matching problem which, as far as I know it, is still only random polynomial solvable, which is the exact matching problem. We have some weighted graph, and you would like to find a matching of size k with maximum. Let me get to a little bit different problem, counting matchings. So we would like to know whether the graph has a perfect matching, but we would like to know how many perfect matchings does it have. So let's recall this identity. On the right-hand side, we will have a summation over perfect matchings. So it's somehow we are interested in the number of terms of that polynomial represented by the determinant on the left-hand side. So how can we find that? Well, a very natural approach would be to try to substitute all ones, because then, of course, every term would contribute 1. The trouble is, of course, with these signs, these plus-minus signs, in the expansion of the determinant. And because if we substitute, we can easily evaluate the left-hand side. That's not a problem, but there's a problem on the right-hand side. And this takes, it's not so easy to overcome. There are two ideas. One is an idea of Hoya, which is substitute +1 or -1 and try to do it in such a way that you sort of compensate exactly for all the signs. So all the terms come out exactly a minute. There's another idea, says that let's substitute randomly and then take expectation, and let's hope that the randomization just takes out these signs, kills the signs. So let's come back to the first idea. That was actually shown to work by Castelline, and a much more recent for planar graphs, which is a celebrated Castelline method for planar graphs, showing that indeed for a planar graph you can always do that. And a characterization of these matrices, this Fourier problem, was recently completed by McKay, Robertson, Seymour, and Thomas. And more recently, this is not that recent. So this is a nice idea which works, but it turns out really the characterization says that this does not go too much beyond planar graphs. So if you get to more complicated graphs, now Castelline was a physicist, and of course he was interested in this mainly because of statistical mechanical models where counting perfect matching is the basic question. And of course, typical material is three-dimensional, not two-dimensional. So planar graphs are not are interesting sort of toy examples, but most often you would like to solve it for other graphs. And that approach doesn't work, unfortunately. The other approach is an approximate computation using determinants, and this is the random substitution idea. Here is the formula. It's a very beautiful formula that gives you the number of perfect matchings. It says substitute randomly plus minus ones, and then take this determinant, square it, and then take the expectation, and this will be exactly equal to the number of perfect matches. So here we have a randomized algorithm. Let's repeat this several times. Take the average. This should be about the right-hand side and number of perfect matches. And that indeed works for many graphs. It does not work for other graphs. Why doesn't it work? Because the variance of this could be so large that you have to generate just too many instances of these random substitutions. So this idea has been pursued for a long time. It turns out that instead of substituting plus minus 1, you substitute the complex numbers, then quaternions, then Cayley numbers, and Clifford algebras, and these all give improvements, but it gets more and more difficult to analyze what's going on. So this is actually an interesting approach, but it's very difficult to answer, to tell what the variance of this is. And without that, you don't know, or don't have a good condition when this may apply.
Is the variance can be described in terms of the graph?
It can be described by counting certain cycles and so on, but nobody really has seen it. So this is a question. So, and finally, I'd like to say a few words about Jerome Sinclair's approximate algorithm by sampling. And in particular, because the way I do it is that alternating fast right back. So get rid of determinants and it gives you methods. So, I still have how much time? 1 minute? So, let's look at the property in NP. And we have seen that the notion of NP already grew out of Jack trying to understand what the main meaning of the König-Egerbarri theorem and the Hungarian method was. But anyway, so a property in NP can be sort of described that there exists some x so that some property ax, y is true. So y has this property if there exists an x, so just ax, y is true, but a is some polynomial time computable property. And the witness to this property is any x that makes this true. Now if you have a witness, such a property, you can ask for a witness, for existence of a witness. You can ask to find an optimal witness, optimization problems, traveling salesman. You can ask the counting problem, number of witnesses. And there is a very basic further problem which is generate a random witness from, say, uniform distribution. And it turns out that this sampling actually is one of the most powerful tools for counting, actually approximate counting. And it's also, of course, used in optimization. Like the whole simulated annealing is really based on this idea that you use sampling for optimization. So we got to sampling. And the idea that sampling could be used in this context is actually, again, comes from matching. So the first really interesting application was the idea of Broder to use Markov chain sampling, to get a random, to generate a random perfect matching. And then a really path-breaking paper by German and Sinclair, they came up with the proof that Broder's scheme works, at least for dense graphs. And their proof is really a beautiful application of alternating paths. And it became the model of many sampling things, and bipartite. But here is the idea, and I want to show the connection with the alternating path. So here is a perfect matching Union graph. And now what we do is we modify this by, well, we delete an edge. I think we deleted some red edge in the middle. And now we try to restore it. And here, look at one of those points which are exposed. And then we add a pick a random edge from it and we put it in. But then we have to delete another edge because we store that it's a matching. And then we repeat this. We pick a random edge from here and delete an edge from here and so on. So we are creating here an alternating path, basically. And we do this until it sort of hits the other point. And then we created a new perfect match. Now the question is how long, first of all, do you get to any other perfect matching eventually, and how long it takes until this mixes. And the main result is that you have to look at the number of perfect matchings compared to the number of these near perfect matchings where only two nodes are exposed. And if this ratio is very small, then it will take very long time to get a perfect matching because you are stuck on this huge inventory of near perfect matchings. On the other hand, if the ratio is larger than 1 over a polynomial, it doesn't have to be huge, say 1 over n to the 10th, then it very often gets, I mean, roughly running n to the 10 steps, it does get a perfect matching. And it's also, this is the harder part to prove that this Markov chain mixes in polynomial time. There's this beautiful theory that Jerome and Sinclair initiated to be able to prove this. And we just finished with the question that we still don't know about non-bipartite, non-dense graphs. So extrapolating the polynomial time matching algorithm, there was a 10-year gap between the Hungarian method and the Edmonds matching algorithm. So based on this, maybe in 1912, somebody will be able to fix this. Thank you.
Bill Jackson and Tibor Jordan taught me something that to me seems so philosophically significant that it should be included in your remarks about matrices of algebra, matrices of polynomials of several variables. They say, and I leave you to confirm, that you can model the local rigidity of a three-dimensional linkage by such a matrix. And for a two-dimensional linkage, we're used to being able to translate that into a deterministic method for the rigidity. And so it's somewhat bothersome not having a translation to a deterministic method. But I think it's a rather beautiful solution simply to model, regard determinants of polynomials of several variables as a solution, you know, as a randomized solution. And so,
yeah, I mean,
please.
It depends what it indeed gives an algorithm. Unfortunately, these algorithms don't give structure, don't give dual solutions, don't give a reason why the property doesn't work. It's indeed true that in 2 dimensions you get for rigidity you get a good characterization. For 3 dimensions, you have this very basic question of whether this determinant is identically 0. And you can indeed decide it in any particular situation, but I think it's still a question whether you can actually point out the reason why. I mean, in 2 dimensions, you can point out that it's always because basically there are not enough bars to rigidify the situation, except maybe somewhere it's overbraced and other parts are underbraced. We don't know for 3 dimensions as far as I know, but it's an absolutely tantalizing open question. On the other direction, if I may mention another question in connection with this, perhaps it's true that this problem of deciding whether a determinant is identically 0 is somehow, in some sense, that's why it could be possibly true that this is complete for randomized polynomial time. But that could be another thing that would be interesting to prove.
Well, with Frobenius as the founder, do you think that there might conceivably be developed a structured theory of matrices of polynomials? A further structural theory. Frobenius started it.
I think there certainly is a lot of room for that. Whether it will be a complete theory or just further interesting classes. I mean, there are many other interesting classes for which this problem is solvable.